All right, so we're talking about elevation versus time. There's another graphing function where we're looking at someone and we're going to graph the story. We're going to label our axis and label our graph as well. So to start out, we're going to watch this video. And then we will, there it is. Elevation versus time. He's coming down the staircase. He stops, take a drink, goes down, continues to walk, goes into the kitchen. We're going to graph the story. Let's look at it at half speed. 2, the time is in the bottom right corner. Let's look at what they got. So they're coming down. And then he stops at about 6 seconds. He stays there until about 8.5. Then he continues down and he keeps walking to the kitchen. 6 to 8.5. Now we're gonna break this problem. So the first part of the question, it goes through and it says, it shows a man climbing down. Let's do the whiteboard now. It shows a man climbing down a ladder that is 10 feet high. So first we need to draw our lines, get a piece of paper and stuff too, so you could start doing this. For all those who are following, we're doing the graphing story 1. Graphing story 1 from the worksheet that we're supposed to do. Assignment for this week. We're gonna label our axes, the y-axis and the x-axis, but what are they gonna be called? And then what's the title of my graph? Red. I think this one was elevation. Yep, I see the chat. And it's in feet. And then this one was time. And it was in the bottom right-hand corner in seconds. And the label of the graph, yes, is elevation times time. These are things that we need to put in. Believe it or not, when you guys get to high school and you're doing this, these are worth a point. Or when you start doing physics, each of these, like labeling the graph, that's a point. The title of the graph, that's a point. Elevation versus time. Please disregard how I'm writing this right now. It's kind of hard to write with the mouse sometimes. And then it says the ladder is 10 feet high. So I'm going to start up at 10. 9. Go ahead and draw this for yourself as well, so you can get the feel of it. 6, 5, 4, 3, 2, 1, 0. And normally you want to space these out with even amount of spaces as well. You don't want to have them crumbled up like how I do right now. So 1, 2, and I think it ended at 15 seconds. Yep. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm gonna make this longer. 13, 14, 15. Keep in mind too that I put arrows at the end of my lines because I'm showing that it's a continuous line, that it keeps going. y. Now, on the worksheet, it says, it shows a man climbing down a ladder that is 10 feet high at 0 seconds. So at 0 seconds, this is the seconds line. So at 0 seconds, his shoes are at 10 feet. So he started at the top. Let's use this right here. So he was right here. And at 6 seconds, his shoes was at 3 feet. So when he gets to here, he was about at 3 feet. So about right here. So I need to go from here. And if you're following on your worksheet, you'll see the question I'm talking about. It's under the graphing story 1 that's on your Google Classroom. All right, so it says his feet was at 10 feet at 0 seconds, but then at 6 seconds, he was at 3 feet. From 6 seconds at 3 feet. From time 6 seconds to 8.5, so from about here to here, 8.5, he drinks some water on the step. So he was at a pause for a little bit. On a step off the ground. He drinks some water on the step at 3 feet off the ground. After drinking the water, he takes 1.5 seconds to descend to the ground. So then he got to the ground, which would be 0 feet. All right. He got to the ground. Which is here. And then he walks into the kitchen and the video ends at 15 seconds. So I have to draw this line all the way to 15 seconds. That's what that looks like. And normally you don't want to go over your graph. Once you've drawn your line, then you don't want to necessarily go over it. So I have this line, a linear graph, and then I have another linear graph, and then another linear graph, and then another linear graph. And when you put them together, you make it a piecewise function. It said 1.5 seconds, so from 6. So from 6 to 7, that's 1.5. So it said from 6 to 8.5, he drinks. I'm trying to see. After drinking the water, he takes a 1.5 seconds. So drinking the water, he takes 1.5. So bam, bam. Okay. So I need to do this part again. Thank you for showing that. Oh my gosh, no. So he goes 1.5 seconds. So from here to about 10. Let's redo that one. Right. Because we went from 6 to 8.5, and then he did 1.5 seconds, so we end up going to 10, and then he went straight to 15 seconds. So that's what our graph would look like. So the first question on there says, draw your own graph for this graphing story. And when you draw your graph, you could put it and make like a sketch. It doesn't have to be an actual graphing system that you use. Make your sketch. If you could take a picture, upload it, send it over to me. Use line segments in your graph to model the elevation of the man over different time intervals. So we have different time intervals because it went from 0 to 6. That's one time interval when he was descending. And then he took a rest from 6 to 8.5. And then he started descending again from 8.5 to 10. And then he was just walking from 10 to 15 seconds. When he landed his foot to the ground, it's right here. Because that's when the elevation is at 0 feet, because he had already touched the ground. So from here all the way over, that's when he's at 0 feet. So that's when his foot touched the ground. The question was, did I get the point where he landed his other foot to the ground too? That other foot doesn't really count. It's just talking about when he touches the ground. So the other foot is not necessarily important at this point. So the first part of the question says, label your x-axis, which we did, time with seconds. Label your y-axis, which we did, which is the elevation in feet. Put this in parentheses. And give us the title of your graph. And the title of the graph is elevation times time. Or question B says, your picture is an example of a graph of a piecewise linear function. Each linear function is defined over a time interval. So all these are different linear functions put together to make a piecewise function. And they're all over different time intervals. All right? Represent the horizontal line. List those time intervals. So we need to list you need to list the different time intervals. Thank you for pointing that out. I had this right here should be X. Let's get this line. Bam. Oh. So we're going to list out our time intervals, and this is question B. Our time interval goes from 0 to 6. All right. 0 to 6. And then the other one goes from 6 to 8.5. And then the other one was 8.5 to 10. And then the other one was 10 to 15, because that's when he started walking. So when we're listing time intervals, this is what they're talking about. The different time intervals for each linear graph that we put together to make the piecewise. Our next question says, C, in your graph, part A, what does a horizontal line segment represent in the graphing source? So it's asking, what does each of these represent? Put your answer in the chat, please. What does each line segment represent on the graph? That's what it's asking. I'll leave that one blank, and then we'll come back to it. Put your answers in the chat. Yep, each line segment represents his movement. It represents his movement. Hope we could understand that. I could also just use a text box. I don't know why. Yep, his movement. The next part, I'm going to start using the text box. The next part, if you measure from the top of the man's head, because this measurement was talking about his feet, all right? Now, if we measure from the top of his head, and he's 6'2" tall, all right? If we measure from the top of his head, how would this graph change? If we measure from the top of his head, how would this graph change? Because he's 6, I want to see some numbers in there too. He's 6'2", right? Let's move back, and then we'll go back to the text. Okay, this is not working out for me, so this is what I'm going to do. I'm going to make this C. And then I'm going to make this D, because it wasn't moving. Let me get some answers. 6'2" is off the ground. The entire graph would basically be 6 feet taller. Its starting point would be 16 feet off the ground. Yes, it would start higher. That is right. It would be higher. The graph would be raised by 6.2 feet. That's basically it. The next question on there is E, a different color, yellow E. It says, suppose the ladder descends into the basement of the apartment. The top of the ladder is at ground level, which is 0 feet, and the base of the ladder is 10 feet below the ground level. How would your graph change in observing the man following the same motion descending the ladder? So he was coming from the attic and he was coming down to the main floor. This time they're asking, what if the top of the ladder was at the main floor, right? And he was going down into the basement. How would the graph change? Do you think that'd be different? The graph would be different because there would be negative numbers, but it still would look familiar. So the graph would look similar, but in a different quadrant. The y values would be negative. And I'm going to show you what I mean by that. So if I had the graph here, remember this goes into 4 parts, right? 4 parts. Right? This part of the graph is what I just blew up. This part, the first quadrant, that's the first quadrant. This right here is the 4th quadrant. It goes 1, 2, 3, 4. All right. So if we're starting at 0, then his graph would come down like this instead. So it would be in the 4th quadrant instead of in the 1st quadrant. Yep, that's what I meant. Look instead of love. Right here. So this graph right here, let me see if I could change it. But this graph is, oh, nope, see, it goes again. Let's put look and see what happens. And then move it. Oh, it's kind of too big. Nope. I don't know. It doesn't allow you to edit after you've written it. That's kind of weird. But anyway, it said it's supposed to be look. Perfect. Now, so it would go into the 4th quadrant instead of the 1st quadrant. Right now we're in the 1st quadrant and it would have been in the 2nd because then it's going to be negative. The next question, which is F. So let's do F. It says, what is his average rate of descent between 0 seconds and time 6 seconds? His average rate of descent. What was his average rate of descent between 8.5 and 10? Over which interval does he descend faster? Describe how your graph part would also be used to find the interval during which he descended. So we need to find his average rate, all right? We need to find his average rate between 0 and 6 seconds. So between this part, 0 and 6, what was his average rate? How would we do that? His average rate. So I'm going to go on a different sheet so that we could, his average, different color. between 0 and 6 seconds. So this is like talking about his speed, all right? And the formula for speed, this is something you need to write down, is distance over time. And that's how we find the rate. It's like when we're driving the car and people say we're going 25 miles per hour. Miles is the distance, hour is the time. That's the rate. In this case, we're dealing with feet and seconds. Are we picking up what I'm saying? When we're in the car and someone's going 50 miles per hour, that's their rate. The miles is the distance, the time is hour. In this case, we're talking about his elevation, which is in feet per second, feet per second. So we need to figure out between 0 and 6. So his distance, I'm going to put speed, but in reality, we're talking about his rate. So his distance between, let's go back. Am I going to be able to edit this when I come back? Let's see. So it says between 0 and 6 seconds. He started at 10 feet, and then he went to 3 feet. So that he has covered 7 feet. So his speed would be 7 divided by, he went from 0 to 6 seconds. All right, so he covered 6 seconds over 6. I needed feet per second. It's not miles per hour. That's when we're doing our driving stuff. In this case, it's feet per second. That's how we find the rate. So speed is equal to distance over time. And they asked for his average rate between 0 and 6 seconds. All right. And he went from between 0 and 6 seconds, he went from 10 feet to 3 feet. That's how I got 7. The next part of the question asks his average rate between 8.5 seconds and 10 seconds. I want you guys to work this one out for me and put it in the chat. So it's asking, what is his average rate? In this case, we're talking about his speed. And I want you to realize that I put my formula every single time I'm going to work something out. Distance divided by time. All right. His speed, which is also the rate. So it's asking for his rate between 8.5 seconds and 10 seconds. So let me go back to the graph. 8.5 seconds, which is here, to 10 seconds. The 8.5 seconds, what was his feet at 8.5 seconds? Let's look and find out what is his feet at 8.5 seconds. 3. Yep. And then what is his feet at 10 seconds? 0. So between 8.5 seconds and 10 seconds, he went from 3 feet to 0. From 8. I'm using the horizontal and vertical so you can understand. So from 8.5 seconds to 10 seconds, he went from 3 feet to 0. All right. So then we're going to go back here. Oh, text box. We're going to go back here and we're going to do the distance. He went from 3 to 0, so he covered 3 feet. And I'm going to divide that by, he went from 8.5 seconds to 10, so he went 1.5. The time between 8.5 seconds and 10 seconds is 1.5. All right, and then whatever that is, feet per second. All right, so then this is really equal to 2 feet per second. So then the question was, which rate was faster? So 7 divided by 6 is 1.16, which is lower than 2 feet. So during his time from here to here was 1.16 feet per second, and his time from here to here was 2 feet per second. So now they're asking which descent part is it this one or this one? Which one was the faster rate? And the faster rate was the second one where he went 2 feet per second. Faster rate happened during the second descent. And that's what F is asking you to do, all right? And with that said, I am going to stop this recording. You could always go back and watch this video, all right? Remember, this is not just a one-time thing. If it's something you don't understand and you need to go back and watch, please go back and watch it, all right?